In the last video, we looked at how to convert color BMP images to grayscale, and in the end, I mentioned how it simplifies our work going forward. In this video, we will start working our way towards constructing an algorithm which takes us one step further towards our goal, which is to build a full-fledged string art generation algorithm. When we try to solve an engineering problem, we don't always experiment with random solutions and adopt the one that sticks. We have a far superior way to make educated guesses using what we call mathematical modeling. In mathematical modeling, we take a problem situation and abstract that situation as a mathematical premise. This helps us get the physical problem into a set of definitions and assumptions which we can work on paper and draw certain conclusions. If you did not understand a word of what I just said, do not worry, you'll be fine. Just follow along and you will see what I am getting at. We have already completed the first step of our algorithm, which is to convert a color image to grayscale and the mathematics behind that conversion. Next, we want to model a couple hundred nails on a blank canvas. And after that, we would be modeling some black threads that run from every nail to every other nail, generating all possible strings that could be strung between any two nails. We could then use those strings to generate interesting designs, including our string portraits. And one more thing before I forget, we will be using pictures with equal side length for this project. If we do not have a square picture, we will use a cropping tool available on the internet to make the picture square shaped. You'll see why I'm doing that as we progress through this series. So let's go ahead and make a blank canvas. We will be developing this algorithm using a blank BMP image as a basis, which is equal in size to the input image. So let's take an input image, do some manipulations on the pixels of the image, and output a whitewashed image that is of the same width and height as the input we started with. To make the canvas, I'm gonna reuse the grayscaling program we wrote in the last video and modify it to make it spit out a blank image of the same size as the input image. In there, we will modify the part where we did the averaging by replacing the average value with 255 so that all the color channels are at their maximum, therefore producing the color white. Let's compile and run this program, and we have a blank image as you can see. Now that we have a blank canvas, we can go ahead and start to think about how to model threads and nails on a canvas. So how do we do that? Well, I'm going to model a nail as just a point on the canvas and a thread that is strung between two nails as just a straight line. Sure, a nail is bigger than just a point and thread isn't exactly a perfect straight line without any fray, but modeling them as simple geometrical objects simplifies the problem very much while still representing the physical manifestation of those objects without much distortion. Okay, that's cool and all, but how do we model points and straight lines on the canvas? Where do we start? I'm going to start by declaring the bottom left corner of the canvas to be the origin, with respect to which we can position points on the canvas. The horizontal arrow in line with the bottom edge of the canvas is what we call the x-axis, and the vertical one which aligns with the left edge of the canvas is the y-axis, and the intersection of these two at the bottom left corner is the actual origin or the 0 point. With this setup, the position of any point on the canvas could be defined by a set of two numbers, one being the offset of the point from the x-axis and the other being the offset from the y-axis. So that's how a point is modeled. The x-offset is called the y-coordinate because this offset is measured along the y-axis, and likewise the y-offset is called the x-coordinate. These two numbers are written as an ordered pair with the x-coordinate first and the y-coordinate second. Together, they can represent any point on the canvas. To model a straight line is a little more complicated than doing it for a point, but it is fairly easy. Let us try to define what it means when we say a straight line. Assume we have 2 points on a canvas. One definition would be that it is the path taken when going from the first point to the second that happens to be the shortest distance between them. Saying so in English seems nice and simple but not very useful for our purpose. Let's see what characteristics does the line possess which could be used to derive a mathematical definition for the line. For starters, the line appears to be inclined at a certain angle to the horizontal and therefore also to the vertical, but we care about just one axis and that's gonna be good enough as we will see in a minute. The line also passes through two specific points, in fact infinitely many specific points, but again we just care about 2 points and that is good enough. Let's assume the line is drawn between 2 points x1, y1 and x2, y2 on the canvas and a third point xy starts at the first point, travels along the line and reaches x2, y2. In doing so, the point xy would travel x2 minus x1 units along the x-axis and y2 minus y1 units along the y-axis. Or in other words, we could say that the point xy has risen by y2 minus y1 units over a run of x2 minus x1 units. I forgot to mention earlier that moving from left to right and bottom to top is considered moving in the positive direction, and the opposite of that is considered moving in the negative direction. That's a very important assumption here, lest we forget. Now, coming back to the line, we can say that the line has a certain rise to run ratio, which is conventionally called the slope or the gradient of the line, which defines how steep the line is inclined to the horizontal direction or the x-axis. We have a simple formula now to calculate the slope of the line if we know any 2 points on it. So now let's go ahead and consider a point xy on the same line. It could be anywhere on the line, even before or beyond the 2 points you see the line is drawn between. It should be no surprise that the slope of the line segment between x1, y1 and xy is the same as the slope of the line segment between xy and x2, y2. So if we equate the two slopes, manipulate the resulting equation a little, we get an equation for the straight line. This equation says if you know any 2 points x1, y1 and x2, y2, then you can find any general point xy on a straight line passing through x1, y1 and x2, y2. That is all it says. For example, let's take the line passing through points 2, 5 and 6, 7. Plugging these values into the line equation, we get y is equal to 1 over 2 times x plus 4, which is the equation of the line passing through these points. The equation basically says that the y coordinate of any point on the line is 4 added to half times the x coordinate. Also, I don't know if you have noticed, but the coefficient of x here, which is 1 over 2, is the slope of the line. That is, the line rises 1 unit for every 2 units of run. And the number 4 is the line's y-intercept, meaning the line intersects the y-axis at y is equal to 4 units. In fact, there is a second way in which you can write the equation of a straight line, which is called the slope-intercept form. Here m is the slope of the line and c is the y-intercept. This is exactly the same equation as before, but looks a little less intimidating. With this, we have mathematical proxies for these nails and threads, and up next, we will put them in their places on the canvas and go from there. So let's go ahead and do that. Before we begin, let us touch upon some basic definitions of trigonometry. In a right angle triangle, if you choose one of the angles that is not the 90-degree angle, the side opposite to that is called the opposite side. That's smart. The one below the angle is called the adjacent side, and the longest side is called the hypotenuse. I suppose most of you know that already. It so happens that if you take the ratio of lengths of any two sides of a right angled triangle and compare that with the ratio of lengths of corresponding sides of another proportionally bigger or smaller right angled triangle, the ratio turns out to be exactly the same. This is a very useful property, and therefore these ratios are given their own names. With respect to angle theta, the ratio of opposite side to hypotenuse is called the sine of the angle theta. The ratio of adjacent side to hypotenuse is called the cosine of the angle theta, and the ratio of opposite side to the adjacent side is called the tangent of the angle theta. Keep this in your mind. We will be using them in a second. Next up, we will derive a model to represent the location of all the nails we would be using. For this project, I'll be putting those nails on the canvas in a circle that touches all four borders of the image. Remember earlier when I said I'll only be using square-shaped pictures for this project, because we will be making a round portrait having a square picture to start with and then fitting the biggest circle in that square wastes very little of that image and is also easy to work with. We will be placing n nails on this nail pitch circle, where n may be 10, 50, 100 or even 1000. We shall determine that number at a later stage, but right now we need n to calculate the angle subtended by any two adjacent nails at the center of this circle. Remember, these nails are spaced equally on it, and since we have n nails spread across 360 degrees or 2 pi radians, the angle subtended by any two adjacent nails at the center of the pitch circle would be 2 pi over n radians. Now let's go ahead and place a nail on the canvas. I'm going to place it at the end of this pitch circle radius right here, which makes an angle theta with the horizontal or the x-axis. So the question now is, What are the coordinates of the nail? Let us say the width of the picture we started with, and consequently the width of our canvas is some W units of length. Since the picture is square shaped, W is also going to be the height of the canvas. This means that the radius of our pitch circle, let's call it R, would be W over 2. Now we shall draw a perpendicular line from the nail downwards till it meets the horizontal radius of the circle, and we shall identify the resulting right-angled triangle with the letters A, B, N. As you can notice, AN is the radius of the circle and therefore has the length R. Therefore, the x-coordinate of the nail is the radius R plus the length of the line segment AB, and the y-coordinate is the radius R plus the length of the line segment NB. So how do we calculate AB and NB? Remember the trigonometric definitions from a few seconds ago? Let us put them to use. We have the sine of theta equals length of NB over the length of NA, and cosine of theta equals length of AB over the length of NA. Therefore, the length of NB equals the length of NA times the sine of theta, and likewise for the length of AB. This gives the x-coordinate of the nail as r plus r cos theta and the y-coordinate of the nail as r plus r sin theta. Now we have the necessary equations to place a nail at any position along the pitch circle. In this project, I will be placing the first nail always beginning at theta equals 0 and the subsequent n minus 1 nails spaced equally across the 360 degrees spread. Therefore, the second nail goes at theta equals 2 pi over n, the third one's at theta equals 4 pi over n, and so on till we reach the last nail, which lies 2 pi over n radians behind the first one, or at theta equals 2 pi minus 2 pi over n. I want you to note that now, instead of using the xy coordinates for the nail, which would require two numbers, I am just using the angle theta, and that is because using theta makes more intuitive sense here, and also conveys the fact that the position of the nail now only has 1 degree of freedom. Now what do I mean by that? Remember, any point on the canvas has two coordinates, x and y. These two numbers are usually independent of one another, but in the case of these nails, the two are not independent and are coupled to a single number, the angle theta. And therefore, any nail has only 1 degree of freedom, or in other words, its position depends only on a single variable. You may argue that x and y depend on the radius r, but I want you to note that r, which is half the width of the image, will remain constant throughout this algorithm and therefore is not considered as a degree of freedom. Not that any of these things matter for the algorithm we are developing, but I just wanted you to know. Now we know how to model a nail, we know how to model a string, and we also know how to model the locations of all nails. We have almost everything necessary to go ahead and start programming nails and strings on an empty canvas. Almost. So in the next video, we will take that knowledge and render some strings on an empty canvas and decide what we can do next.